Hello, chemistry students. This is part 2 of our lessons on stoichiometry. So last time we talked a lot about the mole ratio and how it can be used to compare amounts of reactants in a chemical equation. It can also be used to predict the amounts of products formed in a chemical reaction. In the reality of things in a laboratory, you're mainly going to be working with grams of substances and sometimes solutions of substances, but we'll get to that in another video. So we need to be able to utilize our mass measurements in stoichiometry. And to do that, we're going to need to add the molar mass into our stoichiometry calculations. So let's consider this following reaction. We have CH4, which is called methane. This is the gas that's in a gas stove, reacting with oxygen to make CO2 and water. So this is a combustion reaction. This is usually what's happening when fuel is burning. Um, and if we react 10 grams of this methane in the presence of excess oxygen, so just whatever oxygen is in the air, I want to figure out how many grams of water vapor we could make. So let's get into this. So first, we need to figure out how many moles of methane we have. What our number of grams amounts to, because we can't qualitatively compare chemicals by their masses. We need to convert them to moles first, so we can see what the direct ratio of particles is. So if we take our 10 grams of methane, we divide it by its molar mass, which I calculated to be 16.05, we get 0.6231 moles of methane. And then with that, I can then use all of the mole ratios to determine the other parts that I need to fill out on my BCA table, the amount of oxygen used, the amount of CO2 produced, and the amount of H2O produced. And the ratios are going to be 1 over 1, 2 over 1, and 2 over 1 for carbon dioxide, water, and oxygen respectively. And I get some values here. So since it's 1-to-1 with CO2, I get 0.6231 moles of carbon dioxide being produced. Since it's 2-to-1 for water to methane, I get 1.246 moles of H2O being produced. And then since it's 2-to-1 for oxygen, I get a similar amount of oxygen being used to the water being produced. And I can fill that out on my table. The methane is reacting completely, so we have none of it left. For the oxygen, we started with an excess and we're going to end with an excess, but I still want to fill out the change row to show how much of it is actually being used. And then for CO2 and water, we start with nothing and we form the amounts that we calculated above, and those are our moles. However, like I said before, the moles aren't really useful in a laboratory. So we're going to want to convert those back to grams using their relative or their respective molar masses. So for water, we multiply by 18.02 grams over 1 mole, and we get 22.5 grams of water. And 0.623 moles of the carbon dioxide is going to amount to 27.4 grams of carbon dioxide. And for the oxygen, we can also infer how much of that was used by using its molar mass as well. And we get 39.9 grams of oxygen that was used in the reaction. That doesn't matter so much since the oxygen was just in the air; it was excess. But it's useful to be able to quantify these things. So this reaction created 22.5 grams of water and 27.4 grams of carbon dioxide using the 10 grams of methane that we started with and the 39.9 grams of oxygen that we calculated. Is there anything that you notice about these quantities? Probably not, unless you were taking really, really careful notes on the last few slides. But the reactants, which were 10 grams plus 39.9 grams, that adds up to a total of 49.9 grams of reactants total. If we look at our products, they also add up to the same number. And this is a fundamental truth in physics and chemistry called the conservation of mass. The total mass of the reactants consumed should always equal the total mass of products created. So this is kind of a useful way to check your work at the end, since no matter can be created or destroyed. All right. So we used a BCA table to organize our thoughts in the last one. BCA tables aren't always going to be mandatory. I do want you to know how to use them and how to fill them out, but you can also do these problems without a BCA table like I showed below. Here I just did a direct dimensional analysis method where I just chained together all of my ratios to get to an answer. So to get the grams of water, I just took my 10 grams of methane, divided by its molar mass to convert it to moles, and multiplied by the mole ratio of water to methane. And then finally, I multiplied by the molar mass of water to get the total mass of water. So these kind of have a pattern to them. Usually you're dividing the grams by the molar mass of the first reactant, and then doing the ratio of the product to the reactant, or whatever you're trying to find the mass of, and then multiplying by the molar mass at the end. You can see here I applied the same method to calculate the mass of the carbon dioxide. All right, so in the last example, we did a scenario where we had excess of one reactant. However, if we have specific amounts of both reactants, we need to really consider which one's going to be limiting and which one's going to be excess. So we're gonna do another example of that, and we're gonna do it also with a combination of dimensional analysis and BCA. So we want to figure out how many grams of carbon dioxide are produced and how many grams of water are produced from the reaction of 20 grams of ethane and 60 grams of oxygen. So we have specific amounts. Anytime you're given specific amounts, you need to figure out who's the limiting reactant, because that's going to control how much total product that you can make. So using BCA and dimensional analysis, I start with my 20 grams of ethane, C2H6. I divide by its molar mass and I get its moles. I do the same thing for my other reactant, so my 60 grams of oxygen, I divide by its molar mass. And now I have my moles of my two reactants. And like we did in the last video, where we figured out how much of the other reactant we would need to react with all of it to figure out who's going to run out first. That's what I do down here. So I take my moles of ethane, and I figure out how much oxygen I would need to react with all of it. So in order to react all 0.6649 moles of ethane, I'm going to need 2.327 moles of oxygen, which we could already tell something from this, because this is more oxygen than we have. And then for the oxygen, the 1.875 moles of oxygen, do 2 over 7 for the ratio of oxygen to ethane, and I end up with 0.5357 moles of ethane needed. Now we can compare what we need to what we have. The oxygen needed is more than the oxygen that we have, and the ethane needed is less than the ethane that we have. So therefore, ethane is going to be excess, and oxygen is going to be limiting. So then I can apply that with some more dimensional analysis and some more ratios to fill out my BCA table. So we assume that oxygen is going to be limiting, so it's going to start with our 1.875, and that's going to completely run out, so our change is going to be all of it. And then I can use this number to infer the amounts of the ethane being used and the carbon dioxide and the water being produced using their respective ratios. So I already calculated the ethane, so the change is just going to be the subtraction of the starting amount of ethane and then the amount that we used from the previous example here. And then for the CO2 and the water, I just used their mole ratios, and I got an addition of 1.071 moles of CO2 and 1.607 moles of water. And then I can use their respective molar masses and convert them to grams, like you see here. So this is the dimensional analysis slash BCA way of doing this. Like I said before, you could also do things using just the dimensional analysis, and I kind of go over it here. You can pause the video. I'm not going to explain it because it's kind of the same stuff that I already explained. All right, one more method that you can use if you don't care about the excess reactant and how much you have left over. Another trick that you can do, which is kind of a faster way of doing it, is to figure out which of the two reactants are going to make less of a product, because the one that makes less is going to be the reality. And so how you set this up, so I have 20 grams of the ethane. I do the whole dimensional analysis chain to get 2 grams of water. So if I react all of my 20 grams of ethane, I'm going to produce 35.9 grams of water. Now I switch to the other reactant. If I use all 60 grams of oxygen and I do the whole dimensional analysis chain, I end up with 29 grams of water. And you can see that 29 grams is less than 35.9 grams, which means that this one's the true reality of the situation, and this one is just more of a hypothetical thing if we had enough oxygen to react with all of the ethane. So from there, we can determine that oxygen is limiting, and the 29.0 grams of water is the amount of water actually being produced. And then since now I've confirmed that O2 is the limiting reactant, I can do the same thing for the CO2. I can start with the grams of oxygen and then go through the whole dimensional analysis chain to get to the total amount of CO2. And that is all for this section of our stoichiometry lessons. So I'll see you in the next video.